Hi everyone, welcome back. This is lecture 8. First, quick news. I am now released from the quarantine hotel. Finally got home and I have an iPad now. So from now on, I can use an iPad instead of the crappy writing pad I've been using. Hopefully the notes will be better organized and better written. All right, so for today's lecture, we're going to talk about some applications of double integral. The main application is is using double integral to compute the volume of a solid region. Now, there are, of course, other applications. For example, um, using double integral to find certain populations or to find the average value of a function over some area. But the volume is the main application in here. And this is chapter 7.9 in the textbook. All right. Uh, and also in the last lecture we talked about a simple application of double integrals, which is using double integrals to find the area of regions. Now that is like a baby step application, just because when we're doing that, we kept the integrand 1. So we're not really fully utilizing what double integrals can offer because we're fixing the integrand to be 1. Now, if we allow an integrand to change to be something else, we can use it to find, for example, volume of a solid region. Okay, so today, what we will cover today is like more complicated or more sophisticated applications of double integrals. Now, first, let me give you a direct definition of how double integral is defined when used to express when used to represent the volume of some solid. Let me change. Okay. First, if R is a region in the xy plane, and if f, of course, is a function of x and y, it is continuous and non-negative. Note that we're requiring that function f to be non-negative because when remember going back to say 16b when you were calculating areas under the area under a curve, you need to if the function if the function is not non-negative, then you have to split the function into two parts. The parts where it's negative and the parts where it's positive. You can't just integrate the whole thing, or you can't just integrate the function over the entire domain to find the area underneath it. Okay, you have to split it into two parts. Similarly, here when if f is not if s has negative parts, then you have to do something similar. You have to determine the parts where f is positive and then the parts where f is negative, and then you have to compute these two volumes separately and then add it up at the end. Here, let's just first focus on the simple case where f is assumed to be non-negative over the region R. Then the volume of the solid region between the surface, so an arbitrary surface given by some function f. And f, as we said, is continuous and non-negative over the region R. And R So the region between the surface and the part of the xy plane R. Then the volume is given by the double integral over R Now, dA is just a notation. It doesn't really carry any meaning. It just means we are integrating with respect to area. Now, what is dA? You can't really compute dA. It's not. It's just you should think of it as a conceptual notation. It tells you that we are integrating with respect to area, but how do you compute it? You compute it by using dy dx or dx dy. So I'm telling you that when you see dA, it just means dx dy or dy dx. And here the integral is taken over the region R, and we just put the R, put little r underneath the integral sign. Again, it's a conceptual notation, so it's telling you that we are integrating over this region R. But how do you compute it? You go through the same process we did in the last lecture. You find out the boundaries for this R. You find what's the upper bound, what's the lower bound, what's the left, and what's the right bound. And then you set up the double integral. Say y is from x minus 2 to x squared, and x is from 4 to 6 or something like that. So you can't calculate the area, the integral over a region R. It's not something that you can calculate. You have to go through the same process. When we write integral over region R just to give a general formula for this problem to tell you what exactly this integral is. Okay. Hopefully that all made sense. If not, let me explain this through an example. Let's try to find let's try to find the volume of the solid bounded in the first octant. The first octant is the part where x is larger than 0, y is larger than 0, and z is larger than 0. I mean, larger than or equals 0. Okay, and bounded by the plane two minus x minus 2y. You can easily verify that this indeed is a plane, because if you move everything to the left, you get x plus 2y plus z minus 2 equals 0. And the general form of a plane is ax plus by plus cz plus d equals 0. So this is indeed a plane. All right, the first step to these problems is always to graph it. Graph the plane and graph but here there's only one plane. But if there are more, then graph all of them. This is the y-axis. This is the x-axis. This is the z-axis. Now, how do you graph a plane? As you all should know, a plane is determined by 3 points. So that means if you have 3 points in the three-dimensional space, of course, if you have 3 points, then there is only one plane that passes through all of them. So to graph a plane, the simplest way to graph a plane is to pick 3 points and connect all of them, and that represents a plane. For example, the simplest points to pick here are the intersections with the x-axis, y-axis, and z-axis. let's look at the intersection of the plane with the z-axis. Now, a point being on z-axis means x equals y equals 0. So we have z equals 2. Therefore, the intersection with the z-axis is x equals 0, y equals 0, z equals 2, or 0, 0, 2. Similarly, the intersection on the x-axis is given by 0 equals 2 minus x minus 0, because now b on the x-axis means y equals z equals 0. So once again, you get x equals 2, which is 2, 0, 0. And to find the intersection of y-axis, you let x and z be 0, so you get so you get 0 equals 2 minus 2y, and y equals 1. So this is 0, 1, 0. Now we just connect these 3 points, and this is the plane that we are given. So you need to have a little bit of like three-dimensional imagination. So this is a plane that's covering the corner. Okay, now from the process before, or from the definition before, we know that a double integral over the region R represents the solid bounded between the region R and the surface F. Now here we have F. F is 2 minus x minus 2y. Now, so what is the region R? Here, obviously, region R is the part on the xy plane, right? So this is the region R. To compute the integral over the region R, we need to find the boundaries for this region R. And this is simple to do because if you look at this straight line, this is exactly the trace of the surface on the xy plane. Let's write that down. Trace of the surface, or trace of the plane, on the xy plane. That's obtained by setting z equals 0. So you get 2 minus, 0 equals 2 minus x minus 2y. Therefore, 2y equals 2 minus x, and y equals 1 minus x over 2. So this is the equation for this straight line. And we therefore know that R is bounded between x equals 0, y equals 0, and y equals 1 minus x over 2. Now it's also helpful to graph this region R in a two-dimensional setting. So something like this. This is x equals 0. This is y equals 0. This is x equals 0. And y equals 1 minus x over 2 should look something like this. It's x equals 2 and y equals 1. So, and here is R, and this is x-axis, this is y-axis. Okay, so this space, this shaded area, this shaded region on the xy plane, if we draw it out in a two-dimensional coordinate system instead of a three-dimensional one, then here's the representation for it. Then we set up the area, we set up the double integral. Volume, I'm just going to use capital V here. This is the integral over R, let me just rewrite this, f of x, y, dA, right? Once again, dA is dx dy or dy dA, depending on the order of integration you pick. Here, if you want to integrate with respect to x first, then dA is dx dy. All right. Now, f of xy we know is 2 minus x minus 2y. So that's 2 minus x minus 2y. Now we characterize this region R by y between 0 and this function 1 minus x over 2. So we get 0 to 1 minus x over 2. So since this is the lower bound and upper bound of y, then then that means we're integrating with respect to y first. Therefore, dy dx. And x, as we can see, is between 0 and this intersection. That can be easily computed. Just set y equals 0, you get 1 minus x over 2 equals 0, therefore x equals 2. So that's 2, 0. So that means x is between 0 and 2. Okay, so this is the setup for the volume of this solid region. Let's compute it. Let's compute the inner integral first. Integrating with respect to y, we get 2y minus xy minus y squared. And this thing evaluated from 0 to 1 minus x over 2, and then integrated with respect to x. Plugging these two boundaries, we get 2 times 1 minus x over 2 minus x times 1 minus x over 2 minus 1 minus x over 2 squared. Plug in 0, you get 0. So that's all of the integrand, and then dx. Take apart the parentheses, you get 2 minus x, then minus x plus x squared over 2, and minus, this is 1 minus x plus x squared over 4. Grouping things with the same order, now the highest order term is x squared. So we have 2x squared minus x squared over 2 minus x squared over 4, which is x squared over 4. And the first order terms, minus x minus x minus minus x, so minus x plus x, that means minus x. And then finally constant terms, 2 minus 1, so plus 1 dx. The antiderivative is x cubed over 12 minus x squared over 2 plus x, and then evaluate it from 0 to 2. Once again, plug in 0, you get 0, so you only have to plug in 2. You get 8 over 12 minus 4 over 2 plus 2. Now 4 over 2 is just 2, so it's minus 2 plus 2, so they cancel out, and you're left with 8 over 12, which can be simplified to 2 over 3. Therefore, the volume of the solid is 2 over 3. Okay, let's try another one. Let's look at another example. And in this problem, we will formulate the volume in two different ways. So we're going to interchange the orders of integration, just like we did in the last lecture. You'll see that since if you look at how we solved example 1, you'll find that we didn't really use the shape of the solid anywhere. We really just use what R is like. We describe the boundaries of the area R, and then we integrate it on top of that area. So just like how we use double integrals to compute areas of regions, we can similarly interchange orders of integration when we are finding the volume of some solid. Here's an example. Okay, let's find the volume. under the surface f of x and y equals e to the minus x squared, and bounded by the xz plane and the planes y equals x and x equals 1. All right, as always, the first step is to graph the solid. Now note that in this case, the surface we're given is f of x and y equals e to the minus x squared. Now this is not as easy to graph as the plane example we were given before, because for planes all you have to do is you find 3 points on the plane and then you connect them. You got yourself a plane. But for a surface that's like this, I mean, how do you graph e to the x minus x squared? It's easy to graph when you only have 2 variables. But if you use that as height, it's just not as easy to draw. But we realize that we don't really care what this solid looks like, because we're integrating the height on the region R. So really what we need is the shape of this region R. So all we have to do is to graph R instead of this function f. So let's do that instead. And to graph R, all you need is a 2-dimensional coordinate system, x and y. Okay, so we try to find what this R looks like. So we find all the surfaces that define this solid. The first one is xz plane. Now for xz plane, if you look at the trace of xz plane on the xy plane, then what you're going to get is x equals 0. Sorry, I mean y equals 0, so the x-axis. Because xz plane is defined by y equals 0, so it's like a if you imagine it, it would be a plane coming out of the paper, but perpendicular and intersecting the paper at the x-axis. And then the planes y equals x, again, since it doesn't depend on z, the height at all, it will be a plane that intersects the paper with the curve, with the straight line y equals z and coming out of the paper. This is y equals x, sorry. And then x equals 1 is a straight line like this. I mean, yeah, x equals 1 as a plane is once again a plane that's coming out of the paper. But if you look at the trace on the xy plane, then it would just be the straight line, x equals 1. Okay, and this point has the coordinate 1, 0. And since this is the intersection of y equals x and x equals 1, then the intersection point has the coordinate 1, 1. So we got our region R. This is our R, and f of x and y just defines the height. So we got pretty much everything we need. We got the region R and we got RF, and the volume is simply defined by the integral of f on top of region R. So let's compute that. By the definition, volume is the integral of f of xy on top of R dA, right? Now dA is either dx dy or dy dx. Let's first do dx dy. If you integrate with respect to x, then it means you're going horizontally first and then vertically later. If you're going horizontally first, then for the inner integral, you need to find the left bound and the right bound. Now, if you look at the shape, if you look at the region R, you realize that the left bound is the straight line y equals x, because for anywhere you're going horizontally from here to here, right? So it's from y equals x 2x equals 1. Here's the dotted line. Now, y equals x, of course, is equivalent to x equals y. We're simply interchanging the two sides of the equality. So it means the inner integral has boundaries y and 1. And for the outer integral, we look at the domain of the variable y. So the lowest point of this shape is y equals 0, and the highest point of this shape is y equals 1. So it goes from 0 to 1. Okay, and f of xy is e to the minus x squared dx dy. Now this thing is hard to compute. Because we don't really know what the antiderivative of e to the minus x squared is. In fact, it cannot be written out as a combination of simple functions or just a single simple function. A simple function is like pretty much like a polynomial or e to the something, like anything you can write out directly. But e to the integral of the antiderivative of e to the minus x squared is not one of them. To evaluate this, you actually need like Taylor series. You have to do a Taylor expansion of this and evaluate the integral of each term individually. But that's very difficult computation. So let's see if doing an order of integration can make this easier. Once again, the volume is the integral on R of f of xy. But this time, let's see if we can integrate with respect to y first. Now, if you're integrating with respect to y, it means we're going from bottom to top. If you look at this this is obviously a triangle. The bottom is this line, which is x-axis. So that's y equals 0. And the top of this region is y equals x. So the upper bound of the inner integral is x. And similarly, for the outer integral, we look at the domain of x. It goes from the leftmost point of this shape has x coordinate 0. The rightmost point of this region has x coordinate 1. So it goes from 0 to 1. And plug in our f here. That's e to the minus x squared dy dx. Now this we can integrate because e to the minus x squared doesn't depend on the y at all. So this is just a constant. And we get e to the minus x squared times y evaluated from 0 to x. Now when you plug in 0, you get 0. So it's just e to the minus x squared times x. And to compute this, we need to use u substitution. We write the 0 here. Use u substitution. Let u be x squared. Then du dx equals 2x, or alternatively, du equals 2x times dx, if you will. Okay. Now, when you are doing a u substitution, never mind. Sorry, just forget what I said. The integral is from 0 to 1, and then this becomes e to the minus u times, since du is 2x dx, then x times dx is du over 2. So we get 1/2 of e to the minus u. Now the antiderivative of that is minus 1/2 of e to the minus u. Evaluated from x equals 0, x equals 1. Now note that the original integration was on x, so the 0 and 1 are boundaries for the variable x. We have to substitute x back in, and we obtain 1/2 of e to the minus x squared, and x from 0 to 1. Plug in 1, we get minus 1/2 of e to the minus 1. Plug in 0, minus becomes plus, so plus 1/2 e to the 0. So e to the 0 is 1, so we get 1/2, and minus 1 over 2e. So that's the answer for this problem. We see that we can, just like in the last lecture, we can integrate orders. We can integrate orders of integration. Well, I mean, the interchanging order of integration, it has nothing to do with the specific application of the method. It doesn't matter what you're applying the method, what you're applying the double integral for. For any double integral, you can always interchange the order of integration, and it's the same. It's the same process every time. Here, I'm just showing you how we can use how we can interchange the order of integration to compute the volume of a solid easily. Because if you chose, for example, dx dy first, like we did in this example, you'll realize that's an integral that you can't evaluate. But if you do it the other way around, it becomes immediately simpler. Let's look at another example where the order of integration makes a difference. Example 3. We want to find the volume of the solid bounded above by the surface f of x and y equals 6x squared minus 2xy. And below, by the region R, where R is a region on the xy plane between the two curves y equals 3x minus x squared and y equals x. So unlike the previous two problems, I'm giving you the region R directly. You don't have to come up with the edges of the region R by looking at the traces of all the surfaces. I'm giving you R straight. All right, the first step is, as always, graph the region R. Now R is the region between these two curves. Y equals x is obvious. It is a straight line going through the origin with slope 1. Y equals 3x minus x squared. Since it's a second order polynomial, we know it's a parabola. And since the coefficient in front of the second order term is minus 1, it's a parabola facing downward. And the rest, all you have to do next is, look at the center axis, which is 3 divided by 2, so that's 3 over 2. That means it's a parabola that's symmetric at 3 over 2. You can also look at the height, the peak of the parabola, or the intersection of the x coordinate, whatever you like. After some analysis, you'll find that it's a parabola that looks like this. Not a very good drawing. Let me do it again. Okay, and this is the region R. So this is y equals x, and this is y equals 3x minus x squared. And in between is the region R. So here, to fully describe the region R, of course, we need the coordinate of this point, because we need to know what's the x coordinate of the rightmost point of this region. To find that, we compute the intersection points of these two curves. So the first step, or the second step, the first step was graphing R, intersections of y equals x and y equals 3x minus x squared. To do that, we simply write out the equality x equals 3x minus x squared. move everything to the left, we get x squared minus 3x plus x equals 0, or x squared minus 2x equals x, or equals 0. X squared minus 2x has common factor x, so we get x times x minus 2 equals 0. That gives us two solutions, x equals 0 or x equals 2. And plugging these back into the equations of the curves, we get that the points of intersection are 0, 0, and 2, 2. 0, 0 is the origin, so of course it's this one, and 2, 2 is this point right here. So now we have the rightmost point. Let's come up with the double integral that describes the volume of the solid. Now here, when we are using a double integral, we have to decide whether we integrate in the x direction first or y direction first. Let's see what happens if we integrate with respect to x first. Now, integrating with respect to x means we're integrating horizontally. If we look at this height right here, and going from left to right, the left end is on this curve, on this parabola, y equals 3x minus x squared. And the right end is on this y equals x. So that means the parabola, if it is the left bound of this region R, and the straight line is the right bound for this region R. But if we move it higher, if we increase y, say we're going from here to here, then we find that the left end is on the parabola, and the right end is on the parabola as well. So we're going from the left side, left half of the parabola to the right half of the parabola. That creates a problem. It means that there are two different right bounds of this region. So to correctly compute the volume, we have to split the solid into two parts. We need to compute the volume over this region first, this region, the bottom half first, over the bottom region first, and then compute the region of the compute the volume over the upper region, and then we add these two numbers up to obtain the volume of the whole solid. And that's a lot of trouble, and it can be saved by integrating in the other direction. If we integrate with respect to y first, if we're going from bottom to top, then we realize no matter what x is, the bottom is always this straight line y equals x, and the top is always the parabola y equals 3x minus x squared. So, fine. So this third step is find volume. So we choose, let me first write R and f of x, y, dA first. And f of x, y is 6x squared minus 2xy. So we know that we should integrate with respect to y first. So it's dy dx. Integrating with respect to y, we find the lower bound and the upper bound. The lower bound is y equals x, and the upper bound is y equals 3x minus x squared. So it's from x to 3x minus x squared. So we choose. Sorry, let me write the boundaries for x first. Now x obviously is going from 0 to 2, so we have 0 to 2, and this is the complete this is a complete double integral. All right, and we choose dy dx because otherwise we need to split the solid into two parts. Okay, now if we do dy dx, then one integral suffices. All right, let's compute this. The antiderivative of 6x squared minus 2xy is 6x squared y minus xy squared. And this thing evaluated from x to 3x minus x squared. And then dx, of course. Plug in these. We get, we'll plug in 3x minus x squared, we get 6x squared times 3x minus x squared minus x squared times 3x minus x squared squared. All right, minus brackets 6x squared times x, so 6x cubed minus x cubed dx. We need to simplify this before we move on. Let's take apart all the parentheses. We get 18x cubed minus 6x to the fourth, and then minus x squared times 3x minus x squared squared. That's x to the fourth minus 6x cubed plus 9x squared. And then minus 6x cubed, minus 5x cubed. Oops, I made a mistake here. So this is not x squared, this is x, and that's x. Yeah. Okay. Let's arrange the terms from highest order to lowest order. It's minus x to the fifth, that's this term right here, and then minus 6 times x to the fourth, so we got this term, we got this term. Now this term is minus 6 x cubed, so that's plus 6 times x to the fourth. So that cancels out. And what do we have next? Oh, I missed the dx here. And then the third order term plus 18x cubed, that's this term, and this is minus 9x cubed, that's this term, and then minus 5x cubed dx. Again, this is the integral from 0 to 2 of minus x to the fifth, minus 6 plus 6 cancel out, 18 minus 9 minus 5, we get plus 4x cubed. All right, the antiderivative of this is x minus x to the sixth over 6 plus x to the fourth, evaluated from 0 to 2. Plug in 2, we get minus 64 over 6 plus 16, and then minus 0, because if you plug in 0, you get 0. 16 times 6 is 96, so we get 32 over 6, or 16 over 3. And this is the volume of the solid. So this is once again an example where the order of integration matters. So therefore, for a general problem of finding the volume using a double integral, here is the general outline. Let me see. Okay, here. Oops. Alright, so the guidelines for finding the volume of a solid. The first step is write the equation. Note that the solid is always a solid over the xy plane. So here, right now, we are not looking at just arbitrary solids. We are looking at solids that's bounded between a surface and then the xy plane. So we write the surface in the form z equals f of xy. Going back to the first example, we were given a plane. The first thing we did was we wrote the height coordinate z as a function of x and y, because this f of x and y is what you are going to be integrating. Okay, and sketch the solid region. Now I'm going to add if possible, because for some problems it's just not something that you can simply uh, sketch. For example, like when you have e to the minus xy, how do you sketch that thing? It's just not something you can easily do. Um, so it's helpful if you can sketch it, but if not, it's not the end of the world, because at the end of the day, what we really need is the region R. We don't need to know the shape of the whole solid. We just need to know about the region R, because that's where you are going to be integrating over. Okay, so the second step is sketch the region R. Now this is absolutely necessary. And determine the order and limits of integration. As we saw in the previous two problems, the two example problems, the order of integration, determine the order of integration. Hang on. Yeah, that's perfectly fine. Sorry about that. All right. As we saw in the previous two problems, sometimes the order of integration makes a difference. If you choose a wrong order of integration, you may end up with a double integral that you don't know how to evaluate, or something that's going to cause a lot more trouble for yourself. And limits of integration, it just means the boundaries of integration. I like to use the term boundaries, but limits means the same thing. All right, so the third step, of course, is to just evaluate the integral. And remember to use the order and limits that you determined in step B, step 2. So this is the general guideline. You have 3 steps. First, write out the equation of the surface, and then sketch region R, determine the order limits, and then finally evaluate the double integral. Okay, now let's look at another application of double. Another common application of double integrals is to find the average value of a function over a region. In the one-dimensional case, if your function of one variable, then the average of the function is defined to be the integral of that function over a certain interval divided by the length of that interval. So similarly here, if you want to find average over a region, then you integrate over that region and divide it by the area of that region. So here's the formal definition. If f is, of course, is a function of x and y, is f if f is integrable over the plane region R with area A. Then its average value over R is average value equals equals 1 over A times the double integral of this function over the region R. So this A means the area. It's a numerical value. This dA means we're integrating over an area. Okay, this is a fairly straightforward definition. Let's see how that can be applied in a real-world problem. All right, example 4. Suppose a, oh, let me write this in black. Suppose a manufacturer determines that the profit for selling X units of one product and Y units of a second product is modeled by this function. Since it's profit, we use the letter P instead of the normal function letter F. Where P is minus, or P is a function of X and Y. Equals minus X minus 200 squared minus Y minus 100 squared plus. So here, just by looking at this profit function, we know that the optimum number of units sold is 200 for product 1 and 100 for product 2. If you sell any fewer than that or any more than that, you don't make as much profit. Okay, and then The weekly sales for product A is vary between 150 and 200 units. And the weekly sales what is product A? I meant product 1. Sales for product 2 vary between 80 and 100 units. Estimate the average profit. Okay, so we estimate the average profit by integrating the profit over the range of the weekly sales for the two products and divide them by uh, uh, the range for product A is like the difference for the units sold for product A is 50 units, while the difference for the number of units sold for product 2 is 20 units. So we divide it by 50 times 20 because if you visualize it, it's like the area of range R. If you think of XY. Not if if you think of xy as the xy plane, then we are saying that x goes between 150 and 200, y goes between 80 and 100. So the region R will be a rectangle with one length 50 and the other side length 20. So you get the area of the rectangle is 50 multiplied by 20, which is 1000. Okay, so the average value is average profit equals 1 over 50 times 20, and then the integral from 150 to 200, and then 80 to 100, and then minus x minus 200 squared minus y minus 100 squared plus 5,000, and then dy dx. Here, the order of integration actually doesn't matter. You can try it. You can interchange the boundaries and then do dx dy instead. It makes zero difference. I'm just picking out dy dx instead for no reason really. All right, so this is 1 over 1000 times the integral from 150 to 200. And this is, since the first term doesn't depend on y, we get minus x minus 200 squared times y, and then minus y minus 100 cube divided by 3 plus 5,000 y. and y evaluated from 80 to 100, and then dy dx. Sorry, it's a little cluttered here. I don't want to write out all the calculations here, but if you plug in 180, you will end up with minus 20 x minus 200 squared, and then minus 292,000 divided by 3 dx. All right, and this is 1 over 1,000 times minus 20 times x minus 200 cube divided by 3, then minus 292,000 over 3, evaluated from 150 to 200. This is of course not an integer, just because 292,000 cannot be divided by 3. If you type this into a calculator, this is approximately 4,033. So that means the average profit is $4,033. All right, lastly, let's look at an example on population. So all of these of a region. Oops. What did I do? My bad. Okay. Okay. Example 5. The population density, if we have the population density of the city can be modeled by f of xy equals 50,000 divided by x plus square root of y plus 1. Yep. All right, where x and y are measured in miles. And we want to approximate the city's population. And here is a diagram of the city. This is all ocean. So it's a beachside city, which is nice. All right, and this is 5. This is minus 5. This is 5. This is minus 5, and this is 4. And this is city. Okay, so the city is described by minus 5 smaller than or equal to y smaller than or equal to 5, and of course 0 smaller than or equal to x smaller than or equal to 4. It's a rectangular city. Then since f is the density, is the population density, then the population can be obtained by the integral of the population density over the entire region of the city. Therefore, population equals the integral from 0 to 4 and minus 5 to 5, then 50,000 divided by x plus absolute value of y plus 1, then dy dx. And since we have an absolute value in there, we need to distinguish into two parts. So when y is larger than 0 or y is smaller than 0. And you'll find that it's actually 2 times, or let me just go through the entire calculation. So it's the integral of from minus 5 to 0 of 50,000 x minus y, because when y is negative, the absolute value of y is minus y, and plus 1 dy. And plus the integral of 0, from 0 to 5 of 50,000 divided by x plus y plus 1 dy dx. And this is actually the integral of 0 to 4 times 2 times the integral from 0 to 5 of 50,000 x plus y plus 1 dy. Because if you look at this part, the integral from minus 5 to 0, and if you use some substitution, say let z equals minus y, then you get from 5 to 0 of 50,000 x plus z plus 1 times dy dz dz, where z is minus y. Right, so if z is minus y, then dy dz is negative 1. And if we interchange the upper and lower bounds of the integral, we get another negative 1. So the negative cancel out. We get an integral from 0 to 5 of 50,000 x plus z plus 1 dz, which is exactly the same as this integral. Therefore, we get 2 times that. Okay? All right, so let's compute this integral. This is the integral from 0 to 4. First let's get rid of all the, get rid of this very large constant. let's take it out. Let's take the constant out. We get 2 times 50,000, so you get 100,000. So it's a huge constant at the beginning, 100,000 times the integral from 0 to 4, and then the integral 0 to 5 of 1 over x plus y plus 1 dy dx. Oh, I'm missing the dx here. And this is 100,000 times the integral from 0 to 4 of ln of x plus y plus 1. Note that we don't really need the absolute value here because x and y are both non-negative. And here y evaluated from 0 to 5, and then dx. All right. So this is ln of x plus 6 minus ln of x plus 1. All right, integrate this. You get x plus 6 times ln of x plus 6, then minus x plus 6. This is this is hard to explain why. I mean, it comes from the simple observation that if you differentiate this, you get ln of x plus 6. If you if you differentiate, so I guess here's what you can do. If you have differentiate x times ln of x, you actually get ln of x. Because if you differentiate, because from product rule, you have the derivative of x multiplied by ln of x, which is just ln of x. Oh, sorry, I mean minus x here inside the derivative. And the second part of the product rule is x times the derivative of ln of x, which is 1 over x, so you get plus 1. And then derivative of minus x is minus 1, so you're just left with ln of x. Okay, so here's just a little fact that I put here. All right, and from that fact, we know the antiderivative of ln of x plus 6 is this. And the antiderivative of ln of x plus 1 is similarly minus x plus 1. Maybe I should write this in the second line. Then minus x plus 1 ln of x plus 1 minus x plus 1. This entire thing evaluated from 0 to 4. And this, if you plug these two numbers out, I mean, you get ln's and stuff. So if you want the decimal, you have to type that into a calculator. If not, you can just leave, like for example, 10 times ln of 10 or something. But if you type that into a calculator, then this number is what you will get. It is approximately 4,022,810 people. This is the population of the city. So these are all we're going to talk about today, the applications of double integral. See that the applications, they are, I mean, it's all the same thing. It's just evaluating double integrals. The difficulty lies in finding the correct, formulating the correct double integral. So when you are doing these application problems, you have to understand what you're doing. For example, in this city, I mean, you have to understand that you want to integrate population density, and then the area R will be the area of the city. You want to integrate the density over which where this density is taken. And in the example, of the profit. If you want, since we're looking for the average value, you have to understand that we are looking for the average value over over the possible range of the weekly sales for these two products. Okay, so this is all for today. I will see you on